So hello everyone, my name is Alvaro Lopez Paredes and I am a PhD student for the Center for Session Systems. And this presentation has been, and this work has been developed with Dr. Miguel Heredia Conte. And basically I would like to talk about the codes that we have developed for full-phase time of flight. So first of all, the motivation of our work, then a brief description of the mathematical model, then a step-by-step procedure of the coded demodulation scheme, what is the sensing model, and what are the steps, the way that we think this process, then some implementation in OMP, in sparsity-aware recovery algorithms, the preliminary consideration, research, and some prospective work. So the main motivation is the current time of flight cameras represent an interesting alternative because they are cheap, because their size is low, and because the power consumption is also quite low. However, they have some limitations. The angular range is limited by the optical system, by the field of view of the camera. The depth range is limited by the optical power, and the lateral resolution is restricted by the number of pixels that we have by the pixel count. So what is the objective? Basically, we want to surpass all these limitations. We want to go far. We want to increase up to 360 degrees our camera, and we want to approach real-time operation. They are very demanding objectives. And basically what we have done is develop a prototype and an associated time of flight model to surpass our limitation. Actually, our camera prototype take advantage of the mechanical rotation around the vertical axis to cover 360 degrees and reduce the exposure time to about introduction of motion artifacts. So similarly to this morning, we want to continuously track the depth trajectories that we observe for each single pixel, and like that, decouple the lateral resolution from the pixel count. So actually, we are able to continuously track the depth that each pixel observes. So as we want to approach real time, we want to reduce the number of measurements and we want to reduce the exposure time. So then the topic is of generating goods coded demodulation schemes here. So we want low density codes, and the basic idea for this is to use a combinatorial approach. So generate the location of the non-zero elements in the sensing matrix as using a combination without repetition of non-zero elements. We are going to introduce an evaluation step, and then we are going to include time shifts. So this is the sensing model, the mathematical model. So how a time of flight camera works in pulse-based mode. So we send a pulse that reflects with the target in the sense, comes back, and is correlated with some cross-correlation function. This mathematically can be seen as each correlation between the stem response function and the demodulation function. We obtain a measurement. The assembly of the measurement gives a measurement vector. The assembly of the demodulation function gives the sensing matrices, and then we have a signal that we want to recover the depth and the intensity, that is the stem response function. As the custom binary, as the codes are not exactly, there is transition times, and also the pulse that we send is not infinitely small. We have a system response function that account for these two effects. So the recovery of the stem response function from the measurement vector can be seen as a L0 minimization problem when the sparsity of the signal is considered. It means that mainly all the space is empty and there are only some opaque targets in the stem. So this is the mathematical model, and this is the translation to our camera. We have a hardware, basically we have a compressive sensing oriented time of flight model, and with a clock frequency, and then we generate a number of custom binary codes. At the same time, we generate illumination control signal. This illumination control signal is introduced into a picosecond layer, and then is sent to a driver that basically will reduce as much as possible the pulse width of the illumination signal. Then we send the signal, and in order to cover the 360 degrees, we use a rotary mirror. Then interact with the stem, come back, and then the lens see the pulse and is correlated in the pixel. we obtain a measurement, and then in the software side, we use a sparsity-driven algorithms to recover the assignment. We repeat this process once and again until we have enough measurement and the error is sufficiently low. So some preliminary concepts that for background in modulation. So basically the coherence is given by the maximum absolute value of the inner product in the sensing matrix and of the normalized color of the sensing matrix, and is a representation of the similarity between the different columns. We have the aspect ratio that gives me is the ratio between the number of measurement and the number of rows, and the number of columns. And then we have the density, that is the ratio between the number of non-zero elements and the total number of elements of the sensing matrix, and then the super resolution factor. In the previous slide, you can see that in this one, you can see that we divide each of the elements of the binary function in a number of steps before considering the system response functions. This yields super resolution. It means that we can obtain a finer grid than the number of distinct elements of the code. So the first idea that came into our mind was to use random approaches. So a random binary matrix in which the location of the non-zero element is given by a realization of a random variable that follows a certain distribution, or a Hadamard matrix. A Hadamard matrix plus a posterior rescaling from ±1 to 0, 1. So the problem in here is that there is a variability that is not a deterministic approach, and also that because of the low aspect ratio, we are not able to ensure recoverability. This is a problem and leads to a depth estimation error. So the second step was to use a deterministic approach or a semi-deterministic approach as progressive edge grouts. In progressive edge grouts that works per columns, the location of the non-zero element in the sensing matrices are given by the location that maximizes the local grid of the associated Steiner graph. That basically is the length of the sorted cycle. However, as in life, a sequence of locally optimal solutions may not always yield a global minimum. And in some occasions, we have problems of unitary coherence. As you can see there, when we have a number of rows equal to 14 and 3 non-zero elements per column, we have some cases in which there are a repetition of similar columns. So how can we prevent this? So if we have a sensing matrix, and we want low density, so the basic idea and the most fundamental is to use combination without repetition of non-zero elements. So a combinatorial approach. So we select a check-knock degree, a number of non-zero elements, and then we perform a random permutation of these non-zero elements in the corpus. What happened that in some cases, the theoretical sensing matrix, the cross correlation function is good, but when we consider the transition times, when we consider the real operation of the sensing matrices, we have coherence equal to 1. And this happens because there are coincidence of rising and falling edge on there. But we have a solution for that. So we introduce an evaluation step that is, well, an additional variable that is the matrix of gradients. So basically, we measure the difference between adjacent columns. And as we can see here, we identify the columns with cross correlation equal to 1. And we can correct them by introducing these algorithms. So basically, this works for progressive edge crowds and also works for the combinatorial approach. We have a set of feasible candidates that are the combination without repetition of non-zero elements. And then every time that we add columns, we check the matrix of gradient. If the matrix of gradient, the coherence is equal to 1, we remove this from the set of feasible candidates. Otherwise, we continue the generation of the sensing matrix. Like that, we ensure always that the coherence of the real sensing matrix of the demodulation function that we are going to use is near to optimal. And you can see here that basically we reduce the matrix of gradient, the coherence is always less than 1, and we reduce the number of highly correlated columns. And you can say, okay, but still there you have a column cost correlation equal to 1. But these ones are very close to each other because they are the result of the fine discretization of the spatial domain. So still we have time super resolution. We are able to see beyond the number of distinct elements of the codes. So that's what I'm going home, but no, we still can go further. We cannot reduce the modulation frequency because of the bandwidth, because we cannot introduce more columns because of the hardware limitation. But what we can do is delay one demodulation function to the other. So introduce time shift, and we can work like that in the picosecond range. And we can also optimize this procedure. The idea is to introduce near to optimal shift and maximize the minimum distance between the columns. Because if you think that each column is a representation of the space, what we want is to separate each column to the other and generate these algorithms, as you can see here. So now we take the near to optimal sensing matrix generated via gradient combinatorial approach, and then check all the possible on-grid offset. So we have introduced 10 steps, sub-steps in each binary, in each element of the binary code. We check which one is the one that maximizes the intercolumn distance. And the matrix is the result of this time shifting. And here we are. So we have checked, this is the representation in the 3D hypersphere of the codes. In the gray one, you can see that is the codes without shifting. The green one is the one that we shift. First of all, the first thing that we do is between one row and the other, we implement a uniform shift. The second one is a random shift. And the third one is the near to optimal shift. And we can see that our representation, our algorithms gives the better result. We cover more surface of the sphere and the intercolumn distance is much bigger. And if you don't believe this graph, you can see here. In the x-axis, you can see that is the number of super steps proportional to the super resolution. And in the y-axis, you can see the intercolumn distance. The blue one is without shifting, and you can see how the red, that is the one that we propose, obtain the maximum minimum intercolumn distance. So it's a further optimization of the coherence of the sensing map. And those are the results. In here, you can see that in the first row is the no shift sensing matrix, and in the second row is the sensing matrix with our shift. You can see that the number of highly correlated columns is reduced. So pretty good result. So now that we can see all the procedure from the random approaches to a deterministic approach, and then to the semi-deterministic approach that we produce using a combination of non-zero elements, using low density codes, then we implement the evaluation step to avoid a coincidence of rising and falling edge, and then we implement the type shifting. We check our results via numerical simulation using a state-of-the-art data set. So I am going to present the result for random, for Hadamard derived, and from gradient combinatorial plus near to optimal shift. I use the input parameter that my camera, that the prototype that we are developing takes. So a modulation frequency of approximately for 50 megahertz. Then the repetition frequency at each binary code repeat is 7 megahertz. This leads a maximum range of 21 meters with a resolution of 5 centimeters. And then I took 10 measurements, 10 rows in the sensing matrices, and then 3 non-zero elements per column. Finally, I obtain a super resolution factor in time domain of 6. I generate the measurements, and I apply a VT white Gaussian noise with a signal to noise ratio of 10 decibels. I use OMP, greedy algorithms, and those are basically the results. You can see in the first row is the depth map. Basically, you can see that there are errors, systematic errors at a certain distance in the random matrix. You can see that also we have some error in the Hadamard derivative matrix, and that the errors reduce a lot when we apply our approach. So some conclusions and prospective work. The idea of this thesis was to develop a camera prototype and generate a sensing model consistent with the camera, to increase the resolution, to increase the angular range, and to reduce the estimation error. And we fulfill these objectives. And actually our methodology is, as you can see, is conceptually simple. It's a step-by-step approach. And we have reduced the depth estimation error with a factor of 10, which is 1 order of magnitude with respect to binary codes that are usually used in literature, and also that the estimation error is also less than 1 centimeter in most cases. So what is the processing work? So the idea is to validate this approach with the real measurements. We have almost completed the validation of the time of flight camera prototype, and the next weeks, the next months, we are going to work in the generation of real measurements and in the generation of benchmarks data set using compliant ground truth. So, and we're going to compare with other construction methodologies that are present in the literature, like Hamiltonian code based or Gray code based. Thank you for your attention. Those are the references that I use for this presentation. And I would like to thank the European Union for her support.
Thank you very much for this nice presentation. Before I ask the audience, I have a couple of questions myself. So when you said that you take into account the rising and falling edges, right?
Yeah.
So the dynamics of the system, which orders of magnitude are we talking about? Is that hundreds of picoseconds? Is tens of nanoseconds?
Is the order of nanoseconds.
Nanosecond.
Yeah.
And the other question is, you said that you want to compare later to other codes that are existing in the literature, and what do you expect to get? So what are the advantages of this low density coding approaches to other approaches, like what you cited, the Hamiltonian coding or Gray coding approaches?
Okay, I have a short answer and a long answer. So the short answer is that our codes works as good as them, but always. This is the short one. The long one is that depends on this Gaussian function that we see on there. So the system response function or instrument response function basically is controlled by the width of the optical pulse that we send. So for very small, for very short pulse width, Gray codes are as good as us. Hamiltonian codes performs worse. When you increase the pulse width, let's say up to 12 nanoseconds, 18 nanoseconds, I will say, Hamiltonian codes behaves as ours. So our codes perform as good as them with Gray based codes. With Hamiltonian codes that are other variations, ours are better for short pulse.
And one last thing from my side and for understanding. So if the Gray codes perform similarly to yours, then could it be because in both constructions you explicitly try to avoid the rising and the coincidence of rising and falling edges?
Yes, I don't have a figure in here about how Gray code looks like, but the idea of a Gray code is that you start with a very wide frequency. You basically is like you divide. No, the other way around. Sorry. You see this sensing matrix, for instance, is like you take from 0 to 32 once, from 32 to 64 zeros, and then in the second measurement, you divide in 4, then divide in 8, then you divide in 16, then divide 36. So this way of generating the sensing matrix, effectively what it does is avoid coincidence of rising and falling heads. Ours is a bit more sophisticated, I would say, because every time you check that you don't have any a coincidence that leads to coherent equal to 1. So, yeah.
Okay, thank you very much. And are there questions from the audience? No questions from the audience, no questions from the virtual audience. So I can go on, that's for sure. I got only one. Oh, okay. Then I got to think about it. Regarding the use of this type of codes for this type of problems, so how does this problem relate to the original mission of low density codes? So is there any relationship, or you just use them because of other reasons?
Well, I mean, low density code, basically the complete name is low density parity check code, and the idea is that they are used for error correction. And what we are doing here is detecting the target. So basically there is an analogy between the detection of the target and the error detection in the code.
Okay. And do you expect always your targets to be sparse and the errors?
Account for the sparsity of the sign error we want to reconstruct. So we have only one, or at most 2 targets to recover in the special time.
Okay. Clear to me. So are there any questions from the audience? Is now or never? There is a question. Okay, Logan, please.
Okay, thank you. So I was just wondering here, as far as I understood, you use binary sensing vectors with only 2 values, 0 and 1.
Yeah.
But most of the time, compressive sensing theory, you consider Bernoulli distribution with plus and minus 1.
In the random, you mean? In the random, they are uniformly distributed.
Yep, and the same is true for the Hadamard sensing, the Hadamard transform, which is between plus and minus 1. And so here, don't you think that you could obtain lower coherence, because that's it's better to have low coherence if you modify the sensing to have negative values?
Actually, this is something that we did. This is basically related to the architecture of the pixel. In the time of like pixel, basically you have 2 channels, 2 integration channels or tabs. So they are complementary. When you have 0 in one, you have 1 in the other. So the idea is that we can use the difference between both channels to have 1 and minus 1. I didn't include this because the idea was to, but we performed these calculations, and in the simulation we obtained a further reduction of the depth estimation error when we consider minus 1 plus 1. So you are right, you obtain better reconstruction results with minus 1 plus 1 using both channels. Okay. But there are some trade-off on that, because this assumes that there is no background illumination.
There is no what?
There is no background.
Okay.
So it's not that easy in real scenarios. But this is why I didn't include it here, because this approach is more robust than the other in real operation.
Okay, thank you.